Good morning everyone. So here is my next lecture based on dispersion, and the subject is optical communication and its code is KEC058. The intended audience is BTech and MTech students here. So what we are going to deal in this lecture is about dispersion in fibers, how the dispersion occurs in fibers and what its affects the output and how it affects the output at the other end of the fiber. So what basically is dispersion is? So in general terms, if we discuss the dispersion mechanism within the fiber causes broadening of the transmitted light pulse as they travel along the channel. So due to dispersion, what will happen? Each pulse broaden. Each pulse broaden and it overlaps with its neighboring pulse. So eventually it becomes indistinguishable at the receiver output, and this effect is also known as intersymbol interference. So whenever the light is thrown from the laser or from the LED or laser, we can use any of the sources to the fiber. Then there will be a pulse which is incident on the fiber, and it will goes on the fiber, and then it will have some broadening. So obviously a light has several frequencies, so several pulses are in the fiber, and they are going to broaden themselves and obviously overlaps with each other, and this will affect the output at the other end of the fiber, and this whole process is known as intersymbol interference. So what signal dispersion limits? So signal dispersion limits the maximum possible bandwidth which you can attain with the particular optical fiber to point where individual signals can no longer be distinguished. So it will affect the bandwidth of the fiber. As we know, the bandwidth of the fiber is in terahertz, that is around 10 to the power 13 to 10 to the power 14 hertz. So 10 in terahertz bandwidth. So obviously it limits the bandwidth of the fiber, and for no overlapping of the light pulses down an optical fiber, the digital bit rate must be less than the reciprocal of the broadened pulse duration, that is 2 tau. So we want that there will be no pulse will be overlapping with each other, so we require this equation, that is BT is less than or equivalent to 1 upon tau 2 tau. So where tau is the width of a individual pulse, and obviously if bandwidth is less than or equivalent to 1 upon 2 tau, then there will be no pulse will be overlapping with each other. So that will be in with this help we can have compensating dispersion fibers. So we can easily avoid these dispersion with these equations. So next we have, in digital communication system, information is encoded in the form of pulses, and then these light pulses are transmitted from the transmitter to the receiver. So larger the number of pulses that can be sent per unit time and still be resolvable at the receiver end, the larger is the capacity of the system. However, when the light pulse travel down the fiber, the pulse spread out, and this phenomena is called pulse dispersion. So pulse dispersion is showing in this following figure. You can see in the first figure, that is figure A, there is initial pulses, and the pulses starts to spread when it enters the fiber. So when it enters, there is broadening of the pulses. Then these pulses will getting overlap with each other. Obviously it will broaden beyond some limit, beyond some width. So initially the width is tau, but when they will overlapping each other, then there will be a limitation that these pulses have a width of 2 tau and it is increasing, and that's why it is overlapping with each other, and no longer the pulses, you can see from the last figure that we cannot discriminate ones and zeros, and from the last figure that which the output is 1 or the output is 0. So with this we have to avoid this kind of dispersion, which is obviously a kind of a noise, as we have already discussed in the previous lectures that what is attenuation and scattering. So in the same way, the dispersion is the kind of a noise or the kind of a distortion which can be accompanied with the pulses in the fiber. So pulse dispersion is one of the two most important factors that limit fiber capacity. The other is fiber losses. So pulse dispersion happens because of 4 main reasons. The first one is the intermodal dispersion. Inter means different. So whenever there is different modes, and in between these modes we have intermodal dispersion. So these are also called as modal dispersion or group delay. Next is the modal dispersion is only important in multimode fibers. So intermodal dispersion only occurs in multimode fiber, as the multimode fibers can accommodate multiple modes. So the dispersion happening in these kind of fibers will be intermodal dispersion, because the different modes will get involved and they will travel along the fiber with different velocities. So at the end they will have some delay because they are traveling with different velocity. That's why they have kind of a dispersion which is called as intermodal dispersion. Many different modes propagating in a multimode fiber. Each of these modes take a different path and different length when traveling down the fiber. Another factor is the differing propagation constant, that is beta, associated with each mode. So each mode group velocity is different. So here basically different group velocity or different propagation constant, due to which the intermodal dispersion occurs in multimode fiber. So both factors contribute to modal dispersion. Single mode fiber doesn't have these kind of intermodal dispersion because only one mode exists in single mode fibers. So next we have material dispersion, another kind of dispersion which is also called as chromatic dispersion. And the material dispersion is caused by velocity of the light or its refractive index. So here we have d square n upon d lambda square is not equivalent to 0. So when this condition happens, only in that case there will be a material dispersion or waveguide dispersion. So next is the waveguide dispersion. Waveguide dispersion is a type of dispersion at attributable relationship of the physical dimension of the waveguide and the optical signal. So in optical fibers, this shows as the propagation constant of the mode, and hence its velocity is being a function of a by lambda. So where a is the core radius and lambda is your wavelength. So unlike material dispersion, even if the refractive indices of the core and the cladding are independent of the wavelength, we will still have some waveguide dispersion. So it's basically if d square n upon d lambda square is not equivalent to 0, in that case there will be a dispersion which is called as material dispersion or waveguide dispersion. So next is the polarization mode dispersion. So in polarization mode dispersion is only important in single mode fibers, and also we have to see that material dispersion which is only in single mode fiber. In this case at 1310 nanometer wavelength we have zero material dispersion. So this particular wavelength is called zero material dispersion. So next we have polarization mode dispersion. So it is important in single mode fibers, as it is written here. In single mode fibers only one mode can be propagated. So this mode is actually composed of two different polarization modes or degenerate polarization modes. The electric fields of the two modes are basically perpendicular to each other as shown in below. So we have in the figure that is a violet one and the pink one. So both these modes are perpendicular to each other, and this is the direction of the propagation. So polarization mode dispersion will occur in single mode fibers basically. So these two polarization modes are identical in a perfectly symmetrical fiber. However, in reality there is no perfect optical fiber. So stresses within the fiber and forces applied to it from the outside world causes the refractive index of the glass slightly vary. In the two, that's why there will be two polarization modes also vary because of the propagation constant. So thus these two polarization modes arrive at a slightly different time at the end of the fiber, and due to which there is a delay between these two modes, and this delay is considered as polarization mode dispersion, which is shown in the below figure. So next we have another category of the dispersion which is called as dispersion flattened fibers. So another way to minimize dispersion effects for dense WDM, that is wavelength division multiplexing system, is to reduce the slope of the dispersion curve. So this is called as dispersion flattened fiber. For a particular range of the wavelength, the dispersion is flattened here. So the reduced dispersion curve slope helps to simplify the task of dispersion compensation for these systems with many optical channels. But there are trade-off. An important one is that the dispersion flattened fibers designs tends to have a smaller mode field diameter MFD, which concentrate optical power in a smaller volume. So the increased power density in fiber can cause non-linear effects here. So when you increase the power from the laser, it will definitely cause some non-linear effects in these type of fibers, dispersion flattened fibers. So you can see from the curve that the curve is between wavelength and the dispersion parameter, which is in picosecond per nanometer per kilometer. Here we have a zero material dispersion wavelength that is at 1.3, that is 1310 nanometer. Here we have non-zero dispersion shifted fibers, that is plus part, and it is the non-zero dispersion shifted fibers, the minus part is with the blue lines, and in between both the blue lines and the violet line, we have a darkened blue line which is called as dispersion shifted fibers. So the dispersion shifted fibers is basically from 1.3 micrometer or from 1310 nanometer, the dispersion is shifted to around 1.5 or 1.55 nanometer, micrometer or 1550 nanometer. So the dispersion can be shifted also at a longer wavelength. So if we want to use some wavelength which compensate the dispersion, we can easily use 1.3 micrometer for single mode fibers. For multi-mode fibers, we have to shift these dispersions, because for multi-mode fibers we have there are at different wavelengths. We have to consider the wavelengths here only. So at 1550 nanometer there are dispersion, but there are less losses. So we can easily compensate these dispersion with the help of dispersion compensating fibers or dispersion shifted fibers. So here there is a relation D1 plus L1 plus D1L1 plus D2L2 multiplied by D2L2 is equivalent to 0. So the dispersion is shifted and the dispersion can be compensated with the help of a dispersion special type of fiber which is called as dispersion compensating fiber. At this point 1.3 micrometer or 1310 we have zero material dispersion. You can see that the graph, the violet line, the dispersion is zero, considered as zero here. And for WDM system the dispersion is in between 1.3 to 1.6 micrometer. The wavelength range is 1.3 to 1.6 micrometer. The dispersion, flattened dispersion is shown here with the violet line. You can say that the dispersion is very much flattened. The blue line, the darkened blue line is for the total dispersion is in between the positive and the negative, which is the approximate dispersion curve in between the two blue lines. So what is dispersion compensating fiber? Now in many countries, tens of millions of miles of compensating conventional single mode fibers with zero dispersion near 1300 nanometer already exist in the underground ducts operating at 1300 nanometer. One could increase the transmission capacity by operating these fibers at 1550 nanometer and using WDM techniques and optical amplifiers like EDFA, erbium doped fiber amplifiers. So there will be significant residual positive dispersion. On the other hand, replacing these fibers by non-zero dispersion shifted fibers would involve huge cost. So there has been considerable work in upgrading the installed 1310 nanometer optimized fiber links for operation at 1550 nanometer. So we can use these special kind of fibers, like this is achieved by developing fibers with large negative dispersion coefficients, few hundred meters to a kilometer, which can use to compensate dispersion over tens of kilometers of the fiber in the link. So these fibers tends to have high index difference between core and cladding and often have a small effective area. So the following figure shows the refractive index profile of one of the design. So basically with this equation D1L1 plus D2L2 is equivalent to 0, we have this particular term. So large negative dispersion which can be compensated with original single mode fiber. Large negative dispersion we can consider for D2, and this can be used for compensating your single mode fiber dispersion. So with the help of some length, some dispersion which is very large in negative, and the in length of the fiber is similar to the earlier length, and we can easily have some zero with this equation we can obtain our zero dispersion in that system. So next, what is overall dispersion? The overall dispersion in multimode fiber comprises of both the things, that is the intermodal dispersion and the intramodal dispersion. So the waveguide dispersion or the material dispersion, both waveguide or oblique material and plus your modal dispersion. The sum of both these components will give you the overall dispersion. So it is defined as sigma T, which is sigma C square plus sigma N square, where sigma C is your chromatic or intramodal dispersion and sigma N is your intermodal broadening caused by delay differences between the modes. So sigma S for multimode step index fibers, obviously, and sigma G for multimode gradient index fiber. So the chromatic term will consist of pulse broadening due to both material and waveguide dispersion, sigma C. However, since waveguide dispersion is generally negligible, so here sigma C is equivalent to sigma M. Only the material dispersion is here. So that's why we have this term sigma C, which is waveguide oblique material. So it is sigma W and sigma M. But here the sigma C component, that is the chromatic dispersion component, will be equivalent to sigma M, as sigma W, that the waveguide dispersion is here 0. So next we have the Kerr effect. The Kerr effect is basically the non-linear effects occurring in the fiber. So whenever you increase the power of the laser beyond some limit, there will be different type of non-linear effects going to occur in the fiber. So non-linear effects which can be easily described by the intensity dependent refractive index. So here the intensity is dependent on refractive index, or you can say refractive index is intensity dependent. So are commonly referred as Kerr non-linearities. So the refractive index of the medium results from the applied optical field perturbing the atoms or molecules of the medium to induce an oscillating polarization. So this polarization then radiates and produces overall perturbed field. So at low intensity, the polarization is a linear function of the applied electric field, and hence P is proportional to electric field. Normally for low intensity, this is for low intensity. Of source. But when you increase the intensity, the polarization is not linearly proportional to electric field. It is proportional to some electric field squares, or like this E square. So it has some harmonic components. So you can see, however, at higher optical intensity, the perturbation do not remain linear function. The applied field and thus Kerr non-linearities may be observed. So thus the intensity dependent refractive index causes the intensity dependent phase shifts here in the fiber, and hence for a light propagating in the fiber, Kerr non-linearities resulting in a different transmission phase for the peak of the pulses compared to leading and the trailing edges, pulse edges. So the small core diameter together with a long propagation distance that may be obtained with single mode fibers has enabled the observation of certain nonlinear phenomena at power levels of few milliwatts. These nonlinear phenomena are basically stimulated Brillouin scattering, stimulated Raman scattering, self-phase modulation, cross-wave modulation, and the four-wave mixing. So these nonlinearities are basically due to intensity dependent refractive index, due to which the propagation constant are varying, and there will be a delay difference between the intensities which are propagating inside the fiber, or the modes getting in the fiber. So these type of scattering, which we have already covered in scattering, that is stimulated Brillouin and stimulated Raman, these are also called as nonlinearities, because for this, if you remember, we have calculated the threshold power. The threshold power for both these things, and up to that limit of the power there will be no scattering phenomena, but after a limit you exceed above the threshold thing, there will be a non-linearities occurring in the fiber and the output will get corrupted. So self-phase modulation, cross-wave modulation, and four-wave mixing, these are also non-linearities. So you can see these non-linearities in my later section or later lecture. So in this lecture, we have already covered about how the dispersion and what are the major causes of dispersion, what are the different types of dispersion, how this dispersion can be compensated with the help of the flattened fibers or with the help of the compensating fibers. And lastly, we have discussed about Kerr effect, that how the intensity, if you increase the intensity beyond some limit, there will be obviously some noises which will be introduced in the fiber, and these noises will corrupt your data at the other end of the fiber. So thank you so much. We will meet in the next lecture.